Okay, so now, Le Chatelier's principle could only give us a qualitative nga description or qualitative nga description as to how the equilibrium will react when the system is disturbed. Diba? So you have an equilibrium system, and then we disturb the equilibrium system by changing the concentration, changing the pressure, or changing the temperature. But the equilibrium, but Le Chatelier's principle could only tell us if asa mo shift ba forward or mo shift ba reverse ang equilibrium once ma-disturb siya. Okay? So, it's good that we have that idea na. Because that is the concept man. The Le Chatelier's principle give us a conceptual picture of how the equilibrium will react once the system is disturbed. Now, equilibrium constant expressions give us a quantitative terms regarding the equilibrium nga state sa atong system. So, these are important because they allow us to predict the direction and completeness of chemical reactions. So, si Le Chatelier, just qualitative. We just say it's to the left or to the right. But once we know the value of the equilibrium constant, kung makakita na ganito, no, for this equation, the equilibrium constant is this. We should know, once makakita na ta sa value sa equilibrium constant, we should have an idea as to how the equilibrium will shift once na-change na ang concentration. I mean, na-disturb na ang system ba? Like change in concentration, pressure, or temperature. Okay? So, let's consider this reaction. This generalized equation. W plus X forming Y plus Z. So, as you know, the left side of the equation are the reactants, and the right side are the products, okay? And this double-headed arrow tells us that this reaction is reversible. Now, the K expression, the equilibrium constant expression of this one is the products, concentration of products over the concentration of the reactants. Now, the terms in this K expression involves the molar concentrations if there is represent dissolved solutes. Okay, so the kanang bracket represent molar. So if you have a value of 0.1 in ana, that means it's 0.1 molar. Alright? Okay, so that's concentration of Y in molarity, Z raised to the power of their stoichiometric coefficients in the balance equation. Okay? All over the reactants, the concentration of the reactants. Now, this could be molarity if the components are present as solutions, like aqueous solutions. Okay? Makita man na nato from the balance equation na it exists in the aqueous solution form, or it could be in pure liquid or solid or gas, okay? However, if ang imong reactant if ang imong component kay gases such as katong Haber process, such as that, wherein you have gases, then you can replace this with pressure, or with the partial pressure of each gases. So that would be the pressure of H2, the pressure of N2, and then the pressure of NH3 squared and cube. Okay? So I hope that's clear. Also, if your reactants or if the components are present in liquid or solid form, then the concentration of that will be equal to 1. So, dili na sila mo exist sa imong equilibrium expression. So, for example, imong solvent, ang Z kay solvent to nga water. Water to ang isa ka component. So, C nawala na ang Z dire, di ba? Natoy Z dire ganiha. So, you just cancel that out because that is equal to 1. Kay, di ba? It's moles of water over, if in the case of water, that's moles of water over liter of water, di ba? So, that will just be equal to 1. Alright? Same with solids, okay? So, don't forget these concentrations are in equilibrium concentrations. Equilibrium concentrations. Don't forget that, okay? And that's products over reactants. So, for every reversible reaction, nadyo na siya equilibrium. For every reaction nga ni reach og equilibrium, nagi na siya equilibrium constant. Alright? That is why in analytical chemistry, it's very confusing sometimes. But we have so many constants, equilibrium constants, nga gibutangan ra og specific nga name. But it's still an equilibrium constant. Same method, that's still products over reactants raised to their stoichiometric coefficient. So for example, Kw is just the ion, it's called the ion product constant. But it's still an equilibrium constant. But this is specific, this term is a special name lang for the dissociation of water. So we have H2O, this one. We have H2O which dissociates to hydronium ion and hydroxide ion. So, it's product over reactant, diba? It should be K is equal to H3O OH all over H2O. But then, H2O is the liquid, so it's equal to 1. So, that's why the Kw is just this one. H3O times the OH, okay? Another, we have the solubility product constant. The solubility product constant is for those heterogeneous equilibrium between a slightly soluble substance and its ions in a saturated solution. So, katuning mga i-dissolve nimo in water, but all of them does not dissolve. So, heterogeneous equilibrium. Kay naman kay after the solution reaches equilibrium, you have a solid napakay mga solid nga particles and napakay dissolved in solution. Kay dili man ma-dissolve tanan. Okay? That is why you have a solubility product constant. Kay kana siya nga solution mo reach magyapon siyang equilibrium. So, KSP is just a term for that. That is why when you read a problem, when you answer a problem, you have to picture out what the problem is kanang stating, kanang picturing out your nga as if you're doing that in the lab really helps a lot in solving these problems, okay? So, for example, barium sulfate, this is a slightly soluble solid, okay? So, when barium sulfate dissolves in water, some of it dissociates into barium ion and sulfate ion. So, the KSP for this is supposed to be it's just K, but then because this is solubility product constant, then but because this is kanang dissolution of barium sulfate, then that's why it's termed as KSP. But you can, it's still the same K ha sa pag-solve nimo. So you have barium 2 plus times SO4 2 minus, diba? All over barium sulfate. That's because, diba, products over reactants raised to their stoichiometric coefficients. So barium sulfate is a solid man, diba? It's solid, oh. So that's why it's equal to 1. So it's just equal to this. Okay? And same here. Dissociation of a weak acid or bases. So mana ang property sa acid o base, okay? They dissociate. So for acid, we term it as Ka, the acid dissociation constant. And for base, we term it as Kb, base dissociation constant. So this one, acetic acid or CH3COOH, that's acetic acid. So this is the acidic H, okay? From inorganic, you will learn why that is the only H nga acidic, okay? But for our purpose, you have to know nga this is the acidic H in the acetic acid. So which means that H maura na ang H nga mo dissociate, okay? Mubuwag sa formula sa acetic acid. That is why in the product CH3COOO minus na siya. All right? So when this dissociates, diba? Now you have this. Now, ang liquid dire, since ang water is a liquid, that is why it's missing na sa imuhang solution. I mean, sa imuhang equilibrium constant expression. Okay? So that's still products over reactants. And the same case sa base. So, ang different ra kay base sad ang imuhang reactant sa imong base dissociation constant. Okay? So, gibali ra niya, di ba? Instead nga ang acid nga acetic acid, it's the acetate. It's the acetate, the base, ang nasa reactant. So, that is why you have this as the base dissociation constant. And this is the same with other constants. So, we have a formation constant right here. So, we have a formation constant right here. Mara niya ang slightly different, but it's still the same K, okay? So, we have the complex all over the nickel 2 plus and the cyanide ion, alright? Then, we also have a constant for redox reaction. So, the redox constant, this is what we call as the redox constant. So, it's the same thing. Then, we have the distribution constant, okay? So, everything, kining tanan, these are just specific or special nga terms para sa type of equilibrium. Okay? But, ang formula nila is the same. The K is equal to the concentration of products over reactants raised to their stoichiometric coefficients. And for liquids and solids, it will be the concentration will be equal to 1. Okay? So now let us try to compute the equilibrium concentrations. Okay, and the equilibrium constant of a system at equilibrium. So, we know that at equilibrium, the value of the reaction quotient of any reaction is equal to its equilibrium constant. Take note the word reaction quotient. Okay? So, basically, ang reaction quotient is that if I have this equilibrium, Okay, supposing this, for this reaction, we don't know if it's at equilibrium. So we get the reaction quotient, or which we denote as Q. So the reaction quotient would that is B all over A, di ba? Raised to the power of 1 around duha. So we know that if this system is at equilibrium, then the Q would be equal to K. Kay ang B ani, if that system is at equilibrium, ang B ani will be at equilibrium concentration and also A. Diba? That is why Q would be equal to K. Meaning, if the reaction quotient of that reaction is not equal, if K is not equal to Q, that means that that system has not reached equilibrium yet, or it's not yet at equilibrium. Okay? So let's take, for example, this problem. So on heating, ammonia reversibly decomposes into nitrogen and hydrogen. So this is the decomposition reaction of ammonia. Okay, so this the first step after writing the equation or the chemical reaction is to balance the equation. Okay? Don't forget, the first step is to balance the equation. Now, if a sample of ammonia decomposes in a closed system and the concentration of N2 increases by 0.11 molar. Okay? So that means ni-decrease siya, ang change sa concentration sa imong N2 is 0.11 molar. Di ba? The change in concentration of N2 is 0.11 molar. The final concentration minus the initial concentration, the change is positive because the concentration of N2 increases. Okay? So, let's picture out the problem, ha. So initially, you only have ammonia in your flask. So nara kay ammonia dira. Okay? After some time, ni-decompose ang ammonia and it produced N2 and H2. Now, upon measurement ato, ang N2 was found to be 0.11 molar. So, meaning, from 0 molar, which is initial concentration of N2, from 0 molar, nahimo siyang 0.11 molar. That is why 0.11 molar is the change in the concentration of N2. Diba? Now, from the balance equation, we know nga for every 2NH3, it could give us 1N2 and 3 ka H2. Okay? So, let's write this again. Okay? So, if we assume nga, if we take this as X, if ang change in concentration of N2 as X, diba? Which is equal to 0.11, this value will be positive. Why would this be positive? Because this is produced, diba? Nakaproduce ka og N2. Okay? So, this will be positive 0.11. Now, we know nga for every 2NH3, natay 1 ka N2 nga ma-produce o 3 ka H2 nga ma-produce. Which means nga if na siya na-produce at katong time, at time T, if naka-produce siya og 0.11 molar nga N2 gikan sa 0 molar nga N2 initially, That means this should be 3x, di ba? The concentration of H2 at that point should be the concentration of N2 times 2 low, di ba? And this will also be a positive value. Kay na-produce man pod formation of H2. For NH3, this would mean we have negative 2x of NH3 at equilibrium. I mean, at time t, okay? So this one is negative kay na decompose man, di ba, gi-consume man ang ammonia para mahimong nitrogen ug hydrogen. So the concentration now will be negative 2x and then x, which is equal to 0.11 and positive 3x. Okay? So that means for every 2 mole of ammonia, we produced 1 mole of N2 and 3 mole of H2. Okay? So here, so this is what we just discussed. Okay, so 0.11 m ang concentration sa N2, which is given in the problem. And this one, you deduced this from the balanced equation. Okay? So don't forget negative ang sa reactants kay na-consume man siya. So we just change in N2. We let x be equal to the change in N2. Mao nang ang atong answer diri is negative 2x nya x, which is equal to 0.11 and positive 3x. Kay para masayon siya solvon x kaysa sa change in N2 nga taas kaayo. Okay? So, now we can compute for the value of x using algebra, di ba? Okay, so, mao ni atong gibuhat, class? Okay? So, let's try to compute for the equilibrium constant, ha? So, iodine molecules react reversibly with iodide ions to produce triiodide ions. So, react reversibly, which means that this is a reversible reaction. Okay? If a solution with the concentrations of I2 and I minus both equal to 1 times 10 to the minus 3 molar, before reaction gives an equilibrium concentration of I2 of 6.61 times 10 to the minus 4 molar, what is the equilibrium constant for the reaction? So the technique, class, to solve for equilibrium constants is to make this ICE table. Okay? So mo ni ang reaction, di ba? We have I2 plus I minus to form I3 minus. All right? So from the problem, we know nga ang initial concentration of I2 o I minus is 1 times 10. Initial concentrations both equal to 1 times 10 to the minus 3. So that means ang initial concentration is 1 times 10 to the minus 3 and 1 times 10 to the minus 3. So, of course, wala pa kay product anak, kay initial pa man. So, ang imuharang gimix is kining duha. Ang imong duha ka reactants more na imong gimix. So, that means, initially, 0 pa jud imong product. Okay? So, mo ni ang gitawag natog ICE nga table. Okay? So, ang change ana, before sa equilibrium, ang change ana would be minus x, di ba? Okay, wait. Let's fill in the given first, ang kining equilibrium concentration. So, we were told nga ang equilibrium concentration sa I2 is 6.61 times 10 to the minus 4. Okay? So, that means nga since negative ang di ba na-consume man ni ang imuhang I2 and then na-consume pud imuhang I minus but na-produce ang imong I3 minus. Okay? So the equation is already balanced. Ha? So for every 1 mole of I2 with 1 mole of I minus, you can produce 1 mole of I3 minus. That means kung makakonsume ka og 1x, let x be the consumed. Okay? Consumed 1 mole nga consumed. Okay? So if nakakonsume ka og x, nakakonsume ka og 1 mole of I2, that would be consumption of 1x, okay? Or x. And then, that means, makonsume sa di mo ang I minus. Kay dili man ka maka-form og I3 minus if you don't use I minus together with I2. Okay? So, negative x ang imong change. Ang imo pong I3 minus, of course, because this is produced, ma-plus x po siya. Alright? That means, ang imong equilibrium concentration would be the initial minus x. Okay? So, imong initial kay initially na kaani, di ba? You have this. And na-change siya with this. Nakuhaan siya og x amount of I2. Okay? So, mo nang initial minus the x. And then, imong I minus from the initial concentration of 1 times 10 to the minus 3, na-change pa po siya og minus x. So, you have 1 times 10 to the minus 3 minus x. Okay? And also, for I3, since initially you have 0 I3, you have no I3 in your solution. And then, na-produce man ang I3 by an amount of plus x. So, that means, ang imuhang equilibrium concentration would be x. Okay? Since the equilibrium concentration of I2 is given, we can solve for x. Okay? So, we were told nga at equilibrium, the concentration of I2 is 6.61 times 10 to the minus 4. Okay? So, you have an equilibrium concentration of I2. So, na kay value ani. Okay? That means, you can equate that with 6.61. So, mao ni nga value taken from here. Okay? So, that means, mao man ni ang equilibrium concentration, no? This is the equilibrium concentration of I2. So, you can equate that with 6.61 times 10 to the minus 4. Kay mao man ang iyang it's given in the problem. Alright? Nga, ang 6.61 to the minus 4 is the equilibrium concentration of I2. So, you have a value for this one. So, from that, we can solve for x. So, x will be equal to 3.39 times 10 to the minus 4. So, mao na ni ang equilibrium concentrations. Okay? Ang I2 is 6.61 times 10 to the minus 4. Ang imuhang x is 3.39 times 10 to the minus 4. So, meaning, ay imong I3 minus is 3.39 times 10 to the minus 4. And ang imong I minus, that will be, imong I minus is 1 times 10 to the minus 3 minus 3.39 times 10 to the minus 4, which is equal to 1 times 10 to the minus 3 minus 1 times 3.39 times 10 to the minus 4. That's 6.61 times 10 to the minus 4. So now, you have equilibrium concentrations of all your components na naka-equilibrium concentrations. So, you can now solve for K. So, na nakaani nga values, na nakaani, you can now solve for the equilibrium constant. So, you just substitute it. So, the equilibrium constant at equilibrium is equal to the reaction quotient. Okay? So, that's 3.39 I3 minus all over the concentration of I2 and the concentration of I minus. And the equilibrium constant is 776. So, remember, an equilibrium constant does not have unit, okay? No unit. Okay? Oh, I'm sorry, class. I think this might have unit. Sorry. Kay, this will be squared man. But in equilibrium concentrations, we don't really put the units in solving for equilibrium constants. Okay? This is, the unit can be used in kung nanata sa thermodynamics nga part, because that will be useful in thermodynamics and kinetics. Okay? If we relate that. But for our purpose, we don't put units in the equilibrium constant. Okay? So, you can try this on your own. Okay? There are several problems that I put in your module, and you can try answering them before you look at the solution. Okay? So, you can just use the ICE table. Remember? So, how do you make the ICE table? So, first is you balance the equation. Okay? And then you fill in what is given. So, here, given man ka sa initial concentration sa I2 and I minus. That means you have 0. That means you can conclude nga 0 pa to, because that's the initial man. 0 pa ang imong product. Wala pa kay sud initially. Alright? And then, using the stoichiometric coefficients, you can deduce kanang the change. So, you just use kanang variables ba? Let x be the amount or the number of the moles of I2 consumed. Okay? And then, you can use the stoichiometric coefficients para ma-deduce nimo ang uban nga changes. And then, you add the two, the initial and the change, then you can find the equilibrium concentrations. Okay?